Okay, so welcome back. Apologies for the sudden stopping there of the recording. I wasn't aware, I didn't realise how close it was to the limit of time. So I'll just continue on, picking up from where I left off. I'd almost explained this idea of the three components of this mixture separating at different points, based due to their varying polarities. Remember, I said there's a polar stationary phase and a non-polar mobile phase that has moved along the stationary phase, and depending on their relative polarities, these three components of the mixture, okay, which is illustrated here with a blue and a red and a yellow, will adsorb at different points due to their varying polarities. This one we would probably consider to be the most polar, this the second most polar, and this the least polar. And that is because it is a polar stationary phase, and this one has adsorbed much earlier than this one and separated out. Okay, just moving on to the next slide, which I think just a little ahead. Here we go. So you might be thinking, just looking at this, well, big deal. All we can really do here is identify that this is more polar than that and that's more polar than that. That's not really telling us much about what's in the mixture. It just tells us that there's some things that are polar and there's some things that are less polar. But we haven't really identified at this point what these things actually are, which, as I said right at the start, isn't that the point of analytical techniques, is really to find out, what is actually in various substances or various samples. So at this point, we only just know that there's some things that are more polar than others in this particular mixture. We haven't been able to identify what these things actually are. However, there is a technique within chromatography that allows us to then be able to identify what these things are. And this technique is known, or this concept is known as the retardation factor, or RF value. So the RF value is the ratio of the distance that a component of the mixture moved through the system relative to the distance moved by the mobile phase. Okay, now that might not make a lot of sense to you because it's a little bit wordy and not really showing you, illustrating particularly well what RF actually is. The best way to illustrate RF is to show you a diagram. So the RF value is, as we said in this definition, is the distance a component of a mixture has travelled along a stationary phase through them with the mobile phase, relative to the total distance the mobile phase actually travelled. Okay, so if we look at this diagram, we had a mixture here that was put on the stationary phase, and the mobile phase started to move along the stationary phase at this same point where the mixture is. Well, probably more specifically, the mobile phase started to carry the mixture at that point, which is what we're interested in. So this particular component has travelled all this way and eventually separated out here, where it is finally adsorbed to the stationary phase and separated out. And if we were to measure that, this isn't to scale, but in this diagram it's been measured as travelling 2.1 centimetres along this stationary phase. So it's travelled for 2.1 centimetres before it is actually separated out and adsorbed to this stationary phase. The total distance the mobile phase has travelled, okay, is this distance here. So it's travelled along the stationary phase all the way to this point here and then has been stopped. Okay, it could have probably continued to go, but it's been stopped at this point. This point where the mobile phase has stopped flowing through the stationary phase is called the solvent front. Okay? So we have a couple of key points here: the origin, where the mixture started, the distance that the mobile phase has travelled, where it ends and is finished is called the solvent front, and then where this component has separated out, okay, is the distance that we're measuring. Right? So it's the substance has separated out at 2.1 centimetres, but the entire distance of the mobile phase has travelled along the stationary phase is 2.8 centimetres. Right? So very simply, the RF value is the distance travelled before it absorbs to the stationary phase, or the distance travelled by a component of a mixture before it separates out onto the stationary phase, which is 2.1, divided by the total distance the mobile phase has travelled, which is 2.8. And a simple calculation there would calculate out to the RF value of this particular substance is 0.75. Okay, and you're probably still saying, well, again, big deal. That's just a number. We know that it's separated out at this point. You might tell us it's fairly non-polar because it's travelled a fair way along the stationary phase. That doesn't tell us what it is, and this number still doesn't tell us what it is. It just tells us, the ratio between how far it's travelled along there to how far the mobile phase travelled in total. Okay, so the final part of identifying what this substance may be is these RF values. Okay, have these standard RF values that are calculated for a range of different substances, in fact lots and lots and lots of different substances for any particular stationary phase and mobile phase. So there is a documented and easily accessible range of standard values for different substances, and simply we can just look at this number and find a substance that has the same standard RF, and that would tell us what it actually is. And that is information that you could find there in various reference books, and I'm sure you'll be able to find standard RF values for different substances online. So once we've got that number, we can actually find what is it that has that RF value, and there are resources out there that allow us to do that. Okay, so essentially RF values, once we have that, then there is a way of finding out what the substance actually is. So that's the technique that is used in thin layer chromatography to determine the components within a mixture and what they actually are. Okay, so the first type of chromatography we just looked at was thin layer chromatography. We'll go back to this slide here. Okay, thin layer chromatography, which is again uses a thin plate coated with silica alumina in a liquid mobile phase. There are a couple of other types of chromatography that we're just going to look at. Same principles. Really, it's about how well different components of a mixture adsorb to a stationary phase, but slightly different techniques used. Another type of chromatography is called column chromatography. Column chromatography has a glass column that's packed with small uniform particles that form the stationary phase. The mixture is applied as a layer at the top, and then washed, or otherwise known as eluted, through by the mobile phase. Okay, so again, easiest way to sort of picture that is to look at a diagram. So a column chromatography, we have a glass column. It is packed at the top here with the stationary phase. Okay, so the stationary phase is actually right at the top of the column here. As it mentioned here, the mixture is applied at the layer at the top, and then washed through by the mobile phase. So the mixture is applied here, okay, and then the mobile phase is applied and washed through, and the mixture is carried down the tube through by the mobile phase. Sorry, I did say that this is the stationary phase here. In fact, the entire column is packed with the stationary phase. So again, if we were just to assume that the stationary phase here is polar substances will adsorb and be attracted to the stationary phase in here, and will take longer to come out the bottom here than non-polar molecules. Okay, so we can see that this mixture that was originally blue has separated out into different components based on their polarities, and this substance that happens to be yellow that is travelling the fastest. So you would say that this yellow component of the mixture is less polar and not as attracted to the stationary phase within the column and can be separated out first. So essentially what will happen is the various components of the mixture will flow through at different rates and be able to be collected at different times. So we've got this first component that comes out, this yellow one, and then eventually that will all be removed. Once that's removed, we can get a separate beaker and collect the next component that comes through at a different rate again. So all the different components of the mixture will come through at different rates, and we can separate them out. We would then be able to use further analysis to determine what these different things are. Okay, another type of chromatography is gas chromatography. So this is when we want to separate or analyse a gaseous substance or a volatile substance that has a very low boiling point that would boil very quickly and evaporate very quickly. So anything that is gaseous would be we would use gas chromatography. Gas chromatography, the mixture is introduced into a coiled column containing the stationary phase and is transported through the column by a carrier gas, a mobile phase. So in this case, the mobile phase is a gas. The stationary phase is still a solid. Stationary phases are always a solid substance. As the gas flows through the column, the various components will adsorb to the stationary phase to varying degrees according to their polarity. Same concepts, absolutely same principles. It's around things being more attracted to the stationary phase or the mobile phase depending on their polarity, and therefore exit the column at different times. The time taken to exit the column is retention time. It's called retention time. Sorry, that's misworded there. This can be compared with known standards to identify each substance. So unlike thin layer chromatography, where the value that we calculate is the RF value, the retardation factor, which is the distance travelled by the substance divided by the total distance travelled by the mobile phase, and we can compare that to a known standard. In gas chromatography, we have a thing called retention time, which we can compare to a known standard. Again, easiest way to understand it is to look at a diagram. So here's a picture, I guess, of a gas chromatography setup. So what we would have is our sample, our mixture that we want to analyse of a gas introduced here or injected here. We would have a carrier flow gas in this tank here, or this supply here. That is the mobile phase that carries the mixture through the stationary phase, which is within this column. So we have a coiled column here, and within that column is the stationary phase. So there'd be particles, be material that's packed inside the column, inside the tube. That is the stationary phase. Again, if we were to assume that the stationary phase is polar substances will absorb to the material within the column to a greater degree, and therefore take longer to exit the system. Okay. More less polar substances won't absorb particularly well to this column, and they will exit much quicker. And the time taken for a substance to exit the system and be detected by this detector. So once the substances, the components of the mixture exit the system, they're detected by this detector. The time taken for this to happen is called the substance's retention time. So if it's a longer retention time, and this was polar, that means the substance is quite polar. It would be more polar. If it's a very short retention time, meaning it's gone through very quickly and picked up by the detector very quickly, exited the system very quickly, and has a very small, short retention time, that would mean that it's actually quite non-polar, or having a very low polarity. If this stationary phase was polar, and again, the retention time can be compared to known standards. So then we can identify the substance based on its retention time and comparing it to the known standards that we can find through various resources.